we can say something positive instead of just saying something negative. What I will point out is that if you only restrict yourself to those x values that are positive, like if you forget about that part, then the limit does exist. And so what we do in that situation, we call it a right-hand limit, meaning you're only considering those x values to the right. And I'll notate that by saying limit as x goes to 0 from the right of f of x. That's this f of x, and there's its graph. You're only considering those positive x values. Even though the function's not defined at x equals 0, that limit is still equal to 1, because if you're only considering x bigger than 0, you can still see that those y values just stay constant, stay closer and closer to 1. Same way, limit as x goes to 0 from the left, only considering those negative x values, your y values are staying constant. F of x. That limit's going to be equal to negative 1. So now here's a question. What if we do something a little bit different? What if we define this function? So here I only defined it for x bigger than 0, x less than 0. What if I give it a value at x equals to 0? What if I say that its value is equal to 2 when x is equal to 0? So here's 0, 1, and 2. Let's say that, and here's what the graph of the function would look like. When x equals 0, f of x jumps up to 2. When it's bigger than 0, it's really constant, and when it's less than 0, it's constant negative 1. So then you could still ask the question, what's the limit as x goes to 0 from the right? And you might start to get a little bit turned around, because you might want to say one of two things. You might want to say that the limit doesn't exist because of that jump, or you might want to say that the limit's equal to 2 because of that value equal to 2. Don't believe it. That's a red herring. These right-hand and left-hand limits, they're still equal to 1 and negative 1. The reason for that, you go back to that definition, whenever the x values are close to 0 but positive, those y values are always staying close to 1, in fact, equal to 1 here. So when you're calculating a limit, you don't actually care what the function is doing at the particular point. You don't actually care how the function is defined at x equals 0. You only care about those points that are close by, and you're saying the y values that are close by, they're sneaking closer and closer to 1. So for this function, it's still true that the right-hand limit, the limit with positive values, is equal to 1. It's still true that the left-hand limit, that limit with negative values, is equal to negative 1. But it's also true that f of 0 equals 2. And there's another definition that we use to account for this. So if it's true that the limit as x goes to a point A, in this case I'm thinking about 0, but it could be any point A. If it's true that that limit of f of x is actually equal to the value of the function, that has a special name. You could say that the function f of x is continuous at the point x equals a. I'll just write CTS for continuous. So if the limit as x goes to a of f of x is actually equal to the value of the function f of a, then you say that function is continuous at the point. And this function is not continuous at x equals 0 because the limit as x goes to 0, well, I mean, it's not continuous at x equals 0 because the limit doesn't exist. So if the limit doesn't exist, then it can't be equal to f of 0 equals 2. But even the right-hand limit is not equal to 2, and the left-hand limit is not equal to 2. So there's multiple problems there.